So tonight's focus is going to be on energy. We're going to talk a little bit briefly about energy conversions and energy requirements for organisms to be able to survive and to be successful. So we're going to start first with just what energy is. So energy is just our ability to do work, and it has two basic states. It has potential energy, which is our stored energy, and then it has kinetic energy, which is our free energy, or the energy that is available for movement, for active energy. If you remember these examples that hopefully you've probably seen before, middle school or elementary school, right? The hill, and I've got a boulder at the top of the hill. So that would be an example of stored potential energy. But then once that boulder starts rolling down the hill, that would be an example of kinetic energy. And there are all kinds of types of energy: mechanical, nuclear, chemical, heat. In addition to those, there's also electric, electromagnetic. Heat is going to be important to us since most of our in biology, since most of our chemical reactions are going to release heat. Okay, that's one of the way. That's the way that endotherms are able to maintain their body temperature, is by doing more of these chemical reactions to release heat so they can stay warm. Okay, so we'll be applying this energy kind of throughout some various units. So remember, we're talking about energy in how it's related to biological systems, not in the physics sense. So all of your living systems are going to require a constant input of energy. They're going to need energy, whether that's plants getting energy from the sun, whether that's heterotrophs getting energy from food. But there needs to be a constant input of energy because organisms as a whole are endergonic systems. Okay, I don't know if you guys have come across these in chemistry yet or not. Endergonic versus exergonic. So reactions that release energy versus reactions that require an input of energy to start, right? Endo is in. So endergonic reactions require an input of energy to happen. Exergonic reactions release energy. And so organisms as a whole, that doesn't mean they don't do exergonic reactions, but as a whole, they are endergonic systems, meaning they're going to require this constant input of energy. Okay, well, what do we need all that energy for? Well, we need it to build biomolecules, right? To build up more proteins, to copy our DNA, to build carbohydrates. We need it for reproduction. We need it for movement, active transport. If you are an endotherm, like we are, the organism would need it for temperature regulation. Okay, so we'll talk a little bit more then about free energy at the end and kind of how that can help do those things. So there's a few laws that are associated with energy that cannot be violated. And so we've got the first and second law of thermodynamics here. And the first law of thermodynamics is that energy can neither be created nor destroyed. This is our conservation of energy, our law of conservation of energy. So energy is not created nor is it destroyed. However, it can be transformed or converted or transferred. So it can be changed into different kinds of energy, but we cannot create it or destroy it. Okay? There's this picture over here on the side here with this random man with a lawnmower. Okay? There's a number of energy conversions happening in this picture to allow this lawnmower to move. Okay? You've got the chemical of the gas. Well, this one isn't a gas lawnmower. Just kidding. So you have the chemical energy that's in the person here. So the food that person took in, that they are then breaking down to be able to turn into mechanical energy to push the lawnmower. There was radiant or light energy that was transferred to the grass for the grass to be able to do photosynthesis, for the grass to grow. So light energy that was transferred into chemical energy. So there's energy conservation is happening all around us as we transform or transfer the energy. But again, it cannot be created nor can it be destroyed. Our second law of thermodynamics states that every energy transfer or transformation, so every time we change that energy, that's going to increase what we call the entropy of the universe. Entropy is a measurement of the disorder or the chaos of a system. And so every time that energy is transferred, heat is going to be released. Some of that energy becomes unavailable for work in the form of heat. So as a general rule, heat is energy that is not able to be used for work. It is unavailable for work. So the more heat that the system is creating, the more entropy or the more disorder that's happening in the system. Heat can only be used for work if the system has a temperature difference where heat would flow from a warmer to a cooler area. So that's the only way that heat can be used for work, is again for heat to flow from a warm to a cool area. In living systems, a living system doesn't have warm parts and cool parts. The temperature is uniform. So the thermal energy that's in the system, so anytime these energy transformation occurs and heat is released, that heat will just warm the entire system. And so the heat will cause more molecular disorder, because remember, every time the energy is transferred, that increases the entropy. The entropy is the measurement of the disorder of the system, and you can basically think of the heat as the disorder of the system. Okay? Think of it as your room getting messy, right? You leave one or two things out. You come in and you change clothes before you're headed to practice, and so you throw your shirt and shorts on the floor, and now you've got one or two things that are on your floor. And so the next time you think whatever, and you just throw more stuff on top of the pile. Well, those one or two things that you threw on the floor, that's the heat. Okay? And as that heat continues to build up by more and more things becoming out of place, I'm increasing the disorder of the system. So for a living system to be able to maintain order, right, because this sounds bad, right, but we can't not do these energy transformations, right? We can't not take our food and convert it into ATP. So we're going to be doing these energy transformations, even though they're going to increase the entropy, even though they're going to create heat, which is going to increase the chaos, okay? And so our entropy measurement's going to go up. Living systems help combat that, okay, and help try to maintain order in cellular processes, so by that input of energy. They have to have enough energy coming in so that it can overcome the energy that's being lost, in particular the energy that's being lost as heat. Okay? Think wintertime, right? In the wintertime, a lot of people eat more, okay, because they are doing more chemical reactions to try to maintain their body temperature, to try to create more of that heat. Okay? And so there has to be, though, that constant input of energy to make up for that constant release of energy. Another thing that living systems do to help combat this is they'll couple together energy processes. They'll couple together a reaction that's going to release energy with an action that requires energy. Okay? Like in the example here, we have digestion. So this is food that you ate. And that food that you ate is broken down, and it's going to release energy when it's broken down. And so that energy that's released when that food is broken down can then be used to synthesize something that you need in your body. So in other words, the cells will use an exergonic process. Remember, we used those terms earlier, right? An exergonic process, so one that will release energy, and they will couple it with an endergonic process that will require energy. If there is a loss of energy flow, so if I don't have this pathway happening here, these exergonic reactions feeding these endergonic reactions, then the organism will die. There has to be a way that this energy can be transferred so that the chemical reactions of life can happen. And so as these chemical reactions slow down or stop, that can result in the organism's death. these energy pathways in these biological systems, they're sequential. They're going to go in an order, and they go in this order to help maintain control and help the energy to be efficient, making sure that the energy is being transferred to the correct coupled reaction that it needs to go to. For example, in this picture here, you can see the substrate over here, okay, is combining with enzyme number 1 here, okay, which creates an intermediate substrate, which then combine with enzyme number 2, which creates another substrate, which then combine with enzyme number 3 before I ever get my final end product. Okay, so this is a step-by-step process that allows for it to be controlled and the energy process, the energy transformation to be efficient, not for it to just all be released as heat really quickly, for it maybe not to be coupled to the right reaction. So this is one of those roles of these enzymes, is to help kind of mediate these reactions. It's part of why they are substrate specific, so that they can help mediate these reactions and keep this going on a step-by-step process to help control that flow of energy. So this free energy, this energy that's available to do work, okay, it's always going to be less than the total energy of the system. Again, we need that constant input of energy. Okay, and this is why we don't have enough energy available to do work in our system, available to do the amount of work that we need to do in our system. And as that free energy continues to decrease, you will then increase the entropy. You increase the chaos of the system. Okay? And so biological systems will help transfer this free energy and maintain this free energy to help maintain the order of the system. Diffusion works off of this process. Okay? So let's look at that here. If I've got all these molecules here concentrated on one side of this membrane, they are more organized. And the more organized those molecules are, the more free energy they have. Okay? They can do more work. They can power a concentration gradient better. They have more free energy. Okay? They can do more work. So the result is they're going to do it. They're going to spread out and try to reach equilibrium. Well, as they move from that net concentration to a high concentration, I have an increase in the disorder, right? Those molecules are moving around more. They have more space to do whatever they want. So I actually have an increase in disorder because my concentration has gone down, okay? And then that gives me a decrease in my free energy. So this one has more free energy, and this end product over here has less free energy, less ability to do work because it's actually more disorganized. Those molecules have more freedom and more ability to move around. And so this system, okay, would need an input of energy to help continue to maintain the system. Okay, all right, so I know this is kind of a foreign topic and a little bit of a strange topic to kind of wrap your brain around. Okay, so hopefully you did the practice work with it as well. Okay, and then we'll look at some application of this that I think will help you with this in class.